So to start off, I'll recap what we talked about last time, just using formulas and parameters to drive other parameters. And today I want to delve a little bit deeper into some of the formulas. And if you do have questions, go ahead and type them in the questions box down below, and I will try and remember to look down at those and answer them. So in Revit, we can use our formulas, and as I mentioned before, they can be arithmetic, algebra, geometry, trigonometry. We can also use conditional statements, if and or not, yes or no, and I want to talk about those a little bit more in depth. With our if statements, I'll just bring up a quick example here. If statements, we look at one condition based upon one parameter or just a value, and if it's true, then use this. If it's false, go to the next one. And as you can see in this example, if this is true, then use this 0.05 GPM. If not, move on to the next one. And we can keep stacking the if statements continuously. We can use as many as we want. There is no upper limit to how many if statements we can have. And then we can also provide an AND statement where it would compare the two parameters or two conditions, and they both need to be true. I don't have an AND statement up here, sorry. But they would both need to be true in order for that to provide us the if true statement. With an OR, it would be either one of those can be true for that statement to be true. So the not that I had mentioned, generally we use that with a yes/no parameter. If one option is checked yes, then the other option will automatically be checked the opposite. And then rounding values, we can round them up, we can round them down, or we can just round them up or down if they're more than half. Show you how that is. So starting on line 5 here, I've got heating and I'm sorry, you're right, my screen was paused. To go back, if statements, true or false, and then if true and if false. So moving on to the rounding values. So the top portion is just a straight up if statement, and the following that I have a round up saying, okay, if the heating coil capacity divided by the heating water entering temperature minus the leaving temperature times the density and specific heat. Here at the end, if round up will round it up to the nearest single unit, nearest one. So if we want to be able to round that to 1/10 of a GPM, for instance, we would multiply it by 0.1, round it, or divide it by 0.1, round it up, and then multiply by 0.1 to get it to round to 1/10 of a unit. And we could pick that to be, if we were talking CFM, we wanted to round that up, we would say round up to the nearest 5. We would divide by 5, and then at the end multiply by 5. So going back to our formulas, as I said, there's no limit to the length or complexity of a formula. It's however complex you want to make it. I've seen some pretty in-depth examples, and the tip I've got here: write formulas in Notepad. I mentioned this in the last one. I love that if I select near this starting parentheses, it'll give me my ending parentheses. You know, same down here, it'll give us the opening and closing parentheses highlighted. And the go out to the Revit Formulas for Everyday Usage post. It's a fantastic resource for you. And I touched a little bit last time on lookup tables and how they were mostly relegated to using dimensions, but now we can use numbers. And if you look at line number 1 here on this example, we always want to use size lookup and then the name of the lookup table itself, that parameter, and then the name of the column that we're going to be looking at. Now here's where they differ from conditional statements. This 0 is actually the not statement or not value. So if all of the other conditions cannot be met, it's going to return a 0. This next ceiling module and ceiling module are the column B and column C, and I'll just open up my Excel file, my CSV. So column A is strictly for descriptor. The first parameter or value that you put after that, if not true, that's always going to be column B, followed by column C, D, and etc. as far as you want to go. So we can follow B, C, D all the way up to D. You'll see I've got the air terminal neck velocity lookup value, and I've divided it by 1 feet per minute. So we're making it unitless so we can actually go to our lookup table and find a value. And then we have air terminal neck size. So if that neck size is a value provided by that parameter, then give us our velocity. In this case, velocity pressure. And go back. So we can use our numbers and pull out values to generate and use in additional formulas. And then as you see at the very end of this particular statement, we've put in multiply by 1 inch water gauge. So we're converting that from a unitless value into a united value within our family. So as I kind of mentioned, we've got lookup table. Lookup table name is the name of your parameter, and then the name of the column that you want to be using, followed by the default value, then column B, column C, and you can keep going. And we can make the parameters we're pulling in unitless, and then when we're all done pulling our value from our lookup table, we can multiply by 1 and get our units. The other thing you may have noticed is that we can use the column name, pound number, pound feet, to actually pull out numbers. The more accepted way of doing that is pound other pound number. And you'll notice I have not converted any of these yet. Like my noise criteria column is still pound number, pound feet. I'll get around to it. Now going into schedules, we've got, we can embed other schedules. I kind of demonstrated a space schedule with an embedded air terminal schedule, but we can also use them to provide us conditional formatting. So if something is out of true, then we'll have those cells highlighted. And we can add parameters with formulas. Parameters with formulas can't be changed, but we can also throw in calculated values as we go. So just to demonstrate quickly, here I've got a space schedule with my air terminals all listed out. And I can choose all of the values for my air terminals under the embedded properties. And we can add all these in, sort them, group them, filter them. If we go back to our fields for our spaces, we can take a look at these. We can add additional parameters, and these would be like project parameters. Or we can do a calculated value. And calculated values are really useful if you don't have the parameters in your families already. We could say, okay, this is going to be a common number, and we can either type the formula in here, or we can hit the button and say, okay, give me area, and I'm just going to throw it into parentheses, divide by 1. So I'm going to take that square footage out, and then I'm going to say by actual supply airflow, divide by, and get to the end and divide that by 1 as well. And CFM, give it a name, CFM per square foot. And now you can see we've got a calculated value of CFM per square foot. If we go back and take a look at that calculated value, edit it, you can see it automatically put in that 1 square foot. So these can be really useful for checking things, highlighting things. One of the other things that we can do with the schedule is, if we do have our calculated values that we got back from either train trace, or if you run your calculations inside Revit, you can get your value, and then instead of coming in here excuse me, and populating each of these CFM values by hand, we can actually highlight, select, say highlight and model, hit close, and it's going to have all of them highlighted, and up here I can change them all to say 250 CFM. Tab back to my schedule, and they're all at 250 CFM. If I need to know which ones might be perimeter, I could do the same thing, highlight and model, zoom out, and see whether or not those are perimeter values or air terminals. I'm going to change these all to 300 or 350, and then go back to our schedule, and you'll see I have a difference percentage in calculated versus actual of 43%. And we can take a look at that under the supply airflow check. Go to the conditional formatting, and if it's between -5 and +5 as a percentage, then it'll give it a background color of red. So we can add a lot of really good information within our schedules to provide us checks and balances, and really provide us the information that we need in order to design better. Now if we get back to our air terminal example, you'll see that I'll be using a lookup table that's looking at the length and width and the neck velocity that we're designing. So if we go back to Revit, tab back, you'll see I've got quite a number of lookup tables. Here's my lookup table name, and we've locked that value in. So if we take a look at the neck velocity, our design air terminal neck velocity, we're using 800 feet per minute, and we're looking at the ceiling module size of 24 inches by 24 inches. So you'll see it showing up here, nominal length, nominal width. Or if we look here, you'll see we can scroll down to 800 feet per minute in column D, 24 by 24, and then the neck size. And where's my neck size? Neck velocity. Okay. Neck radius. Here we go. Sorry about that. So we've got air terminal neck size down here. That's pulling information based upon either we have a next size override up on the top, and if that's greater than 0, then use that air terminal next size override size. If not, let's go to the lookup table. And we're using a conditional statement here. Here, I'm just going to copy and paste this out. So we're using a conditional statement here that if the supply airflow is less than what we're returning out of the airflow column, give me a 0. Otherwise, take a look at this, and if it's that 6-inch column, then, or 6 inches within that column D, then return that value. So this is one of those that can get really convoluted pretty quickly because we're using a conditional statement along with our lookup table and then moving on. So we've got all the way up to a 15-inch neck with several really complex and embedded lookup tables or conditional statements. Now in the VAV, we're using parameters and lookup tables and conditional statements. So we can pull in sizing data, the CFM maximum from our connected air terminals, and then we're calculating our CFM minimum based upon that. And then from there, we can calculate our Q or MBH and CFM minimum and delta T. Then we can, from our GPM, we can get GPM from that Q that we got earlier and the delta T water. And we can also calculate our KW from MBH. Now a quick discussion on how Revit uses units. There is a master unit for every particular type. So let's say you're trying to calculate BTUH. Well, the master unit is going to be watts. So if you're trying to do a calculation on a particular family, let me get back to my VAV, you'll need to divide by, I'm trying to recall exactly what watts is. I think you have to multiply by 0.2937 watts in order to get your BTUs to come through. And conversely, you'll notice GPM, the master unit for GPM is CFM. So in order to get this particular heating coil water flow unitless, we had to divide it by 0.13 CFM in order to make it unitless. So there's a master unit for every type of unit within Revit. Just be aware that if your values aren't coming out right, make sure that when you divide by 1, Revit was actually using the correct unit. And if you try and change it back, Revit's going to automatically swap it back out. So just be aware of that. So in this example, we're looking at the supply air duct connector diameter, and we've got our neck size, and column A is giving us the model number. We can discharge height, discharge width. We can control all of these parameters based on that lookup table. So some quick examples from the heating coil capacity. These are your everyday, daily formulas. You use these all day long. So save yourself some time and put these in your families using the correct parameters, and it's going to save you a ton of time. Like especially down here we got the full load amps. We're taking our heating coil capacity, dividing it by 1 volt, because that's given in watts. So if we take watts out, we're left with amps. And then we're going to take our voltage divided by our voltage and divide the voltage by 1 volt to make it unitless. And then we're taking phase. If our phase equals 1, then use 1. Otherwise, use the square root of 3. Take all that and divide it by the power factor. So it might look a little complex, but these are things you do every day automatically. And we can then take our minimum circuit ampacity and multiply it by 1.25. So quick talk about temperature. Whenever we put in a temperature, we always get this minus 459.67. Oh, looks like I got a question here. Converting Revit master. Question was, do you have examples of conversions numbers for converting Revit master unit to a unitless value? Yes. For instance, if we're taking this particular heating coil value, I'm just going to go copy real quick. I'll make a new one. And I'm going to make that a number. Instance. Okay. So if I put this in here, I'm going to get inconsistent units. And if I divide by 1, it's going to automatically put in CFM. And that's not correct. So I would have to come in here, and I know the conversion of CFM to GPM is 0.13. So back to temperature. This one's, it's always fun trying to figure out our delta T. Because if I were to come in here and take my heating coil entering temperature, paste it up here, and then my leaving temperature, copy, subtract, I'm going to get 429.67 degrees below 0 Fahrenheit. So in order for that to actually work, we actually need to come in here and add 0 Fahrenheit. And you'll notice Revit actually added the proper units back in, and now we're back to 30 degrees Fahrenheit. But if you wanted to do it unitless, I'll show you here, the unitless value, we actually have to get a little more convoluted, multiply those two values by 459.67, and then we divide it by 0. So it took some playing around to figure out what it was that Revit was actually looking for in order to get that 30 as a number that we can use elsewhere. So that's a quick discussion on temperature, and as you may or may not know, temperature's base unit is Kelvin, and what Revit is actually seeing and how do we convert it are pretty different. So here's the example: 180 minus 160 is 439. So what Revit is seeing is it's converting the 180 to 160 to Kelvin, converting 160 to 1 Kelvin, and then subtracting it, and then converting back to Fahrenheit. So here's the what I just showed you with the units, and how do we get back to either united or unitless. Now, a quick note on the Revit 2017. This is the same family that we were looking at earlier with the connections and calculations. And I'm trying to find where, so if I take this same calculation that we used for our delta T and drop it in here, 0 degrees is not valid. So they've made it quite a bit different. There was one other one. Oh, that one seemed to work. There was another value here that it had gone through and did a subtraction, addition. Where did that go? No, now I can't find it. It looked like it was doing some something different. It was subtracting a negative 459.67 degrees. See if I expand this a little bit more. There it is. So it's doing some goofy math where it's automatically adding the 459, I mean double minus, so it's adding 459.67 degrees, and then it automatically at the end of the calculation added a negative 459. So I'm a little baffled by what's going on in 17. I'm hoping this is going to get fixed. Let's see, and that's the leaving dry bulb. So if we took a look at this VAV, and where's my leaving dry bulb? Heating coil, leaving dry bulb. So it's quite a bit different than what we've got right here. So with that, that's the end of it. Just kind of a caveat to what's going on in 17 with temperatures. You might get some funny results, or at least some funny formulas if you were to cut and paste or just open your families. And with that, if there aren't any other questions, that's the end for today. Thank you.